I hadn't seen what was so compelling about string theory. I mean, okay, people say you sort of point particles, think of strings. Okay, fine, you can think of it, but why should I? I mean, but the large N, the ideas of a Thoft, and then what David was trying at the time, and so on. I think those appeal to me much more, and I think that's in a way been a theme of my work.
The guest of today's podcast is Dr. Rajesh Gopakumar. He is a theoretical physicist and the director of ICTS Bangalore and majorly works on holography, CFTs, topological strings, and related areas. So let's talk to Dr. Gopakumar about his life in physics and listen to what he has to say. Welcome to the podcast, Dr. Gopakumar.
Thank you. Thank you very much, Hassan. Pleasure to be here.
Okay, so before we talk about anything else, I recently saw your paper where you were trying to, get strings from Feynman diagrams, and there you were, mapping Feynman diagrams to Riemann surfaces, which come from string theory. I want to ask you about that project, and I also want to ask you that what are the other projects that you are currently working on?
Yeah, no, thanks. I think it has been a long-term goal of mine to understand why string theory is a very natural framework for understanding fundamental physics. And I feel that maybe people often see string theory as some abstract theoretical construction that some people have dreamt up, and everyone is studying it because, and there's a lot of polemic and other stuff going on. But I feel it should be possible to understand why strings come out very naturally from some of the frameworks that we already understand very well, namely like quantum field theory. Um, and quantum field theory, as you all know, is something which is now what we use to describe the fundamental interactions, things in condensed matter physics. It's a very solid, tested framework. Uh, and and I feel strings arise very naturally from it in a way which goes back to, I usually call it like the Faraday picture versus the Maxwell picture. The Faraday picture, in terms of extended lines of flux, is actually a kind of prefigured this idea. And in fact, in the strong interactions, that's how strings arise in some ways from the flux lines of the quantum chromodynamics. So this is why I feel gauge string duality in general is a very broad phenomenon. It's a very it's a very universal phenomenon which cannot be just tied down to the ADS-CFT correspondence or some special cases like that. It's, I think, something much more general. And one of my goals has been to try to understand how general it is and to try to derive the string duals to gauge theories, large N gauge theories, systematically, starting from the field theories, but from a somewhat unconventional point of view, namely starting from perturbative quantum field theories, the things that one understands through Feynman diagrams, as one studies in a course on quantum field theory, around non-interacting theory, a free theory, and so that might at first sight seem a little counterintuitive because people often think of the gauge string duality or ADS-CFT in the context of strongly interacting gauge theories being dual to a gravitational description. But I'm essentially focusing on the other end, which is about looking at the string theory that emerges from weakly coupled gauge theories, weakly interacting gauge theories. And that one believes that that string theory also is something very special. In fact, it's a very special limit of string theory, the so-called tensionless limit, and that, I think, makes it a very natural point to study the string theory too, and not just from the strongly coupled viewpoint. So so this is one place where I feel one can directly see the strings emerge from the gauge theories, and why you can kind of derive the string theory from the gauge theory. So that's been my goal, and I think this paper that you referred to is in along those lines. It's um, doing it for a very simple set of gauge theories, if you wish, namely matrix integrals, matrix models, zero-dimensional gauge theories. And but these are at the same time some kind of a subsector of physical Yang-Mills theories, or any super Yang-Mills theories. And so I think the lessons one draws from here are more general. But nevertheless, the simplicity of the context gives you a chance to explore these in more detail and say more concrete things. And that's one of the reasons why we've studied in this paper, this model in a bit of detail, and fleshed out some of the general features which I think are part of this duality. And one central theme, I think we emphasize, which I have been actually trying to sort of uh, uh, propose for a long time, is that each Feynman diagram, in a sense, can be also viewed. Each Feynman diagram of a gauge theory can also be viewed as a world sheet of a string theory. And that's the sense in which the Riemann surfaces of string theory arise very naturally from the Feynman diagrams of the field theory. You kind of can glue the Feynman diagrams through this process of open-closed string duality to give you the world sheets of the string theory. So in a way, takes the ideas of 't Hooft on large N gauge theories being string-like to more kind of a precise level. And of course, still in a very simple context where we have been, I think, we are able to take this quite far. It's also similar to the example that I had studied a few years ago with Lawrence Eberhardt and Matthias Gaberdiel on the tensionless limit for the ADS3 CFT2 duality. So all these are examples. I think I'm hoping that we'll see a general pattern emerging from these, which is along the lines that I mentioned earlier. And so that's the broad goal. I don't know if that answered the first part of your question
It did.
about what the context and the general goal of this paper is. Uh, I've also been working with Matthias Gaberdiel and others um, on tensionless limits in string theory, in both for the ADS 5 times S5 case, which is the one that's dual to the super Yang-Mills theory in the ADS safety correspondence, and another different sector of the ADS3 CFT2 duality as well, which we had studied one particular limit in our earlier work. We're now trying to understand in some other limits some of these special, whether one can actually derive these dualities in other special limits. And the idea is to start from these and then try to build from there the more general duality.
Right. Okay. So the works that you are mentioning with Gabriel, I mean, we will come back to them in a moment because that's something that I want to discuss in detail, later. But this paper that I referred to, in this paper, you also found this thing that a particular closed string description has 6 different open string descriptions, right? So, and then there is another well-known example of this topological gravity that has 2 open string descriptions for a given closed string description. So what I want to ask you is that, do you think that the number, so we do know that all of these open string descriptions are, equivalent, but do you think that the number of, open string descriptions has some significance?
Yeah, no, it's a good question. This is an idea which I didn't mention, which in this paper we have been fleshing out about this open-closed open triality. Initially, it was a triality, but with 2 open string descriptions and 1 closed string description. that was in a sense for the simplest case of matrix models where it's very naturally kind of between two different sets of brains. In general, I think it's a question of how many different brain configurations you can have. I don't know the full answer to the question, but my guess is that it has to do with the number of inequivalent brain configurations you can use to back react and create the geometry. There could be multiple ways to do this, and there could be multiple stacks of brains which in a sense have the same closed string dual. But and how many stacks there are is is probably dependent on the theory a bit, because and the geometry and the background and how many inequivalent kind of stacks you can have. So for instance, you might have brains extended in different dimensions, different directions, and brains of different dimensions themselves, D3, D5, D1 brains, etc. So you might have multiple such brains, all kind of all being equivalent in at some level. But their number may depend on the theory.
So okay, so now I want to ask you about how you got interested into physics. So this is a question that I have asked almost every guest that appears on this podcast, and previously I used to think that there are small number of sources of inspiration for people to come into physics, but later I realized that no, I mean different people have very different stories. So what was your inspiration to come to theoretical physics?
So I think it's if I really have to, I mean, I was interested in mathematics, and I was interested in, I think, in middle school in chemistry, actually. I used to try to have a chemistry lab. I mean, I just enjoyed that when I learned about chemical reactions, and then I saw some of them. So I tried to play with those. So I think I enjoyed chemistry. This was maybe in eighth grade or something. Seventh, eighth grade, I used to really be fascinated by that at that time, but also mathematics, but there were two parallel things. But then I think afterwards, maybe in ninth or 10th grade, as I learned more about, the periodic table and atoms and so on, I wanted to understand more about what those where how people understood them. And I think that's when I learned about the quantum theory, explaining the atoms, the periodic table, and the different shell structures of the atom. So it was all very fascinating, very mysterious, and quite amazing that everything you see around you, all the elements are made out of just of about 100 or so basic building blocks, and which themselves have a very structured organization in terms of these shells of electrons around a nucleus. So the quantum theory and so on was very fascinating. In fact, it's funny in a sense because I found that more fascinating than the classical mechanics that used to be taught in our textbooks, which was more about pulleys and levers and inclined planes and stuff like that, which, okay, I mean, and maybe I think physics as it was taught in school didn't particularly appeal to me. It was, I think, the chemistry and which led to atomic this thing that was fascinating to me. At the same time, also mathematics, and I could see in these arrangements of these atoms that there was some very that mathematics was really playing a role in our understanding of nature. So then as I read more, and there were many popular science books I read. I think in my high school, the books of George Gamow on 1, 2, 3 infinity, and even some of the Feynman lectures, I think, then really gave you a sense for what physics is as a framework, and it's not just some inclined planes and pulleys and some other problems which seemed quite unmotivated and not particularly interesting to me. And so I think, and in a way, I oscillated a bit between mathematics and physics, but I felt, physics is where you can sort of have the best of both worlds, where you
Sure.
both understand nature and also see the beauty of mathematics.
Sure. So you went to IIT Kanpur for your, undergrad in physics, right? I have to ask this question because, this is a pressure that a lot of people who come to physics from the Indian subcontinent face. So did you feel the pressure to go to engineering?
Oh yes, I mean that was the thing, that was the done thing for everyone in my generation who had some interest in science or who were, so to say, doing well in school. Definitely, I think it was either engineering or medicine that was more or less the career choice for everyone in the subcontinent. Probably now it's a little better. There are many more things people do, um, but yeah, that was there. But I think my parents were supportive, and many people were a little surprised that I was going to an IIT, but not doing the conventional thing of studying engineering there.
Sure. Okay, so I've seen that a lot of people, in India who, work in high energy physics and especially in string theory, they have some kind of a connection with IIT Kanpur. So, uh, do you know why is that? Does IIT Kanpur provide a much better environment for physics as compared to other IITs, or is it something else?
I think what you say is very correct. IIT Kanpur, I think, has had a very disproportionate effect in theoretical physics and the impact it has made in Indian to people who are trained in India. It is, I think, a historical accident of some kind, and it was true for a certain period of time. Also, I think I should add probably till I mean, even now, IIT Kanpur produces some very good physics students, and that continues. But I think till maybe the 2000s or so, there were very few undergraduate programs in India where you could really get a very solid physics sort of an education. There were a couple of colleges, and in fact, initially I was in the city of Kolkata, so there were some historically good colleges there, but there were many issues with the colleges. There were many political sort of turmoil and other things that used to disrupt college. So people probably very correctly felt that that's probably not the best place to study physics at that time. I'm talking of the late 80s, early 90s. And so IIT Kanpur, I think if you left out some of these colleges, there were some in Delhi, Bombay, Kolkata, Chennai, and so on. But if you left out a handful of these colleges, there was essentially IIT Kanpur and IIT Kharagpur amongst the IITs, which had a physics undergraduate program. It was actually a 5-year master's program. And IIT Kanpur was set up in a very unique way. It was set up with the help of the United States, and it was modeled on Caltech and MIT. And while many of the IITs focused almost exclusively on engineering, I think IIT Kanpur, because of this US connection with Caltech, MIT, etc., they felt that it was important to have pure sciences, a strong pure sciences program, both in the faculty as well as for the students. So they actually had gathered some very good physicists and also mathematicians in the early years, in the 1960s when it was set up, and many people who had been trained at some of the very best places in the world, they came back and they had a lot of idealism, and they taught courses with a lot of sincerity and passion. So I felt that so IIT Kanpur, that way, I think amongst people who wanted to do physics, it probably had developed a reputation of being a place where you could go and get a very good physics education. And there weren't many places like it at that time. Now there are many ICERs, there are the IIT, CMI, IASC. There are many, many places now in India where you can get a good physics education. And Yeah, but at that time there wasn't, and I think that's the reason why, at least before a certain generation, most of the people in theoretical physics you see who studied in India, I would have probably spent some time in IIT Kanpur.
Okay. So you went to Princeton for your PhD and you did your PhD under David Cross, right? And the time when you were at Princeton, it was the time of this duality revolution in string theory, right? So correct me if I'm wrong, but I have seen you, claiming on some at another place that you started as a skeptic of string theory. But then, now you have worked a lot on string theory. So how did that transition happen? Because whenever that happens, I'm very interested in finding out the thought process of the person who went through this transition. So how did that transition happen?
Yeah, so I think it is because I was, I mean, quite fascinated by the structure of quantum field theory. I think, I mean, you study quantum mechanics and you study quantum field theory. So I think when I applied to graduate school, I mean, I of course knew of string theory and heard of string theory, but I think I have a little bit of a tendency to kind of be skeptical of when something is hyped up and so on. And there was always a bit of that, but of course, so when I applied for graduate school, I more or less wanted to do quantum field theory related things. I wanted to keep an open mind about string theory in some sense, but at least what little I had seen or this thing of it didn't greatly appeal to me at that stage, at least the things that people were studying at that time. Um, and But when I went to Princeton, David Gross uh, was actually working on the string dual to two-dimensional Yang-Mills theories, and that was something I think. And so, in a way, that's been my lifelong theme. That, as I said earlier in the talk, why do you have to think of strings? What are these strings? Why not think of something more complex, membranes, whatever? And people do think of those, but that's they don't have the same central role that strings have. And what makes it very natural? I mean, because it's very easy for someone to construct some kind of a theory of something, but I think for it to have a compelling nature, you need to have more reason to see its interconnection with other things. That's what makes it compelling. I mean, otherwise, you can always create in isolation something which is a sparkling diamond, but if it's not connected with something, everything else, even theoretically, I don't mean just about experiments, even theoretically, if the interconnections aren't there, then it's not so compelling to me. I mean, so I didn't realize I didn't hadn't seen what was so compelling about string theory. I mean, okay, people say you so point particles, think of strings. Okay, fine, you can think of it, but why should I? I mean, but the large N, the ideas of a Thoft and then what David was trying at the time and so on, I think those appeal to me much more, and I think that's in a way been a theme of my work. So my PhD was actually on the large N limit and the concept of the master field, and so it had almost no string theory in it. In fact, zero string theory in the thesis itself. But I learned string theory in a way it was unavoidable in Princeton. And as you said, the duality revolutions happened at that time, as they're called, and I learned more about it. And at that time, a lot more of string theory was beginning to come together. And then I think and then yeah, so that and the connections with large N started coming out more clearly through the BFSS and then the gauge string dualities, etc. So it all started coming together for me in some ways, and it started coming together for the subject also in terms of the interconnections it was able to make. The Weinberg-Witten theory, gauge and strong weak coupling dualities, both with quantum field theory and string theory, there were very big synergies. So that appealed to me.
Okay. So
Uh,
the thing is that after having so much work done in string theory, we still don't understand, correct me if I'm wrong, but we still don't understand the fundamental degrees of freedom of string theory. So if somebody asks you the question that what is string theory, that is not an easy question to answer. But if I ask you this question, what answer would you give in the light of our current knowledge of the subject?
Yeah, I mean, so we had a KITP program. I think you're probably alluding to that as well, called What is String Theory, which was in turn inspired by an article by Joe Polchinski. So who in turn was inspired by Ken Wilson, who asked about what is quantum field theory. So of course, even in quantum field theory, it took a long time to understand what quantum field theory was, and perhaps it is only after the work of Wilson and others, which came maybe 50 years after the founding of quantum field theory, 40 years maybe. Uh, so uh, so it takes a while sometimes to really understand the essence of what you are trying to figure out. So I think the program that we ran last year, there were lots of people. We were all trying to kind of figure out different pieces of an elephant. I think there is this old story from India about the six blind men and the elephant. I often talk about it. So it's like you're all trying to piece together the elephant, and each one sees a different part and views the elephant in a different light. But so we still don't can't see the elephant. But I feel string theory is a very natural framework which generalizes quantum field theory to be able to include gravity. And it kind of subsumes quantum field theory, but yet at the same time extends it. And in that sense, it's a um, very versatile framework. But what it actually is, I think the answer is still very open. But it is quantum field theory on steroids. I mean, it's that's one way to say it. Maybe it's a kind of a very big boost and upgrade of quantum field theory to make it almost uh, uh, very different, makes it very different, but at the same time grows out of it in a natural, organic way.
Right. Okay, so let me ask one question that may arise in the mind of some young student. The question is that, okay, why do we have to ask that what are the basic constituents of string theory? Aren't they just strings and brains? Don't we know that they are strings and brains? So what would be your answer to that?
Yes, at some level, you have strings, and you know that there are collective excitations called branes, but those seem to be the perturbative degrees of freedom, meaning they are the ones that when the theory is weakly interacting, those seem to be the degrees of freedom that you would excite. Uh, but as we have learnt in quantum field theory, what may be the perturbative degrees of freedom may not be the full non-perturbative description of the theory. And in the non-perturbative description, you may have very different excitations, which you can't directly see from the perturbative picture. So in string theory, we don't have this non-perturbative description in a complete way. We have maybe some glimpses of it in M theory or in ADS-CFT and so on, but we don't know. We don't have M theory is in a sense just a word at this stage. We know only some features of it. We don't really have any kind of a definition, even at the level of string theory, which at least is perturbatively defined. Um, and I think we have learned about some aspects of perturbative string theory, and that too about a limited class of backgrounds. Whereas you would think that if you have a full non-perturbative framework, it should be able to it should be able to tell you what is the whole class of string theories you can study, what different backgrounds can you have, and how are they connected, how are they related non-perturbatively. We are very far from something like that. So it's like your the strings and the brains are little ripples that you're seeing around the solution of string theory that you are studying. But those you're not seeing the full landscape. You're only seeing the small a small region around the particular small corner of the theory. So I don't know if that makes sense, but it's yeah. So there is clearly a vast set of string backgrounds, and people have been studying more of these. The different kinds of string theories, non-perturbative, strong-weak coupling dualities. We don't really have an inkling for why these are there and how to understand them from some first principles.
Okay. So I have one question. So since we don't have, a fundamental description of string theory, any question about that particular description can be answered only by using an educated guess, and that's it. So one question that I have in my mind is that, okay, so what do you think that will the fundamental description of string theory have space-time as a fundamental thing or not? So what is your guess about that?
Yeah, that's actually a good question, and my personal hunch is that you will not.
Okay.
That space-time itself there'll be even the string theory, the degrees of freedom in terms of which even the string theory will be formulated will not be necessarily the space-time degrees of freedom. And that's why I'm a little suspicious of the simple-minded picture of thinking about a string in some simple target space, and that is, I mean, that's of course a simple class of theories, but whether that's representative or that's sort of the generic kind of string theory, I would a feature of string theory, I wouldn't be so sure. It's a bit like when you study perturbative field theories, you see some small corner and you see of field theories and field theory phenomena. But when you study the larger landscape of quantum field theories, you see all kinds of interesting effects, confinement and various symmetry breakings and other things which lead to newer excitation. I mean, a completely different description of the physics. So similarly, space and time, you might think might be some kind of composites that come out from uh, an underlying description. And at some level, ADS-CFT hints at that. Um, because the description in terms of the quantum field theory is very far from uh, being in terms of the space-time. The space-time emerges in this holographic way. So holography, in a way, is a suggestion, I think, that the degrees of freedom shouldn't be thought of directly in terms of space and time.
Okay.
That, yeah, those should be some kind of a composites.
So do you think that it may be a matrix model or something like that?
That's if you were to think of it in terms of a holographic description, a matrix model, at least for a class, we know for classes of spacetimes, it is that's one non-perturbative description. But there could even be a non-perturbative closed string description, and my hunch is that that might be closer to something like a twister string theory or something like that. That it's some kind of a different degrees of freedom, like these twister degrees of freedom that capture
Okay,
space-time. Mm,
I see.
uh, uh,
So
which may have a dual description in terms of some matrix model or some this thing. But even the closed string description might be more natural in terms of other variables.
I see. Okay. So now I want to discuss the work that you have done in the last, 20 years or so on holography. But to start this discussion, for some of the junior, listeners in this audience, can you briefly describe what is the idea of holography? Just briefly, not a lot of detail.
Yeah, so holography is the idea that a theory of quantum gravity in d spacetime dimensions, uh, so in some number of spacetime dimensions, the number of degrees of freedom are actually far fewer than would be in a quantum field theory of that spacetime dimension. The number of degrees of freedom necessary to describe gravitational phenomena in d space dimensions is that of a d minus one dimensional theory, one lower dimensional theory. Uh, and that is the one of the strongest hints for that is, of course, from the black hole entropy formula of Bekenstein Hawking, that the entropy that you associate to black holes, and this is a universal formula in all kinds of spacetimes, not only anti-de Sitter, or a flat space, are always proportional to the area of the horizon. And so the number of degrees of freedom in these gravitational systems seems to grow like an area rather than a volume, or d minus one dimensional rather than d dimensional, which is unlike any other thermodynamic system in which the area is the entropy is always extensive, and therefore grows with the volume. So holography is this idea that there should be another description which captures the degrees of freedom in terms of this d minus one dimensional theory. It captures the quantum gravity description in terms of a d minus one dimension.
So one of the earliest concrete, I think the first concrete example of holography was, engineered by Maldacena, right? Where you have ADS5 cross S5 on one side, and on the boundary you have this four-dimensional n equals four super Yang mills. So in this particular example, there are some very important features that go into making this example. One of the features is that n equals 4 super Yang mills is a conformal field theory, right? Which means that it has this scaling symmetry. And you also have this large n as the thing that you were talking about before. So n can refer to as the number of colors on the gauge theory. But the thing is that I have seen some people, actually a lot of people, work. So they use holography to study something like QCD, and that bothers, I don't know what's the word that I want to use here, but that surprises me because QCD is neither a CFT, and N is 3 for QCD, which is not large. So how do you use holography to understand QCD? If you can comment on that.
So there are two things I would say. Firstly, I think the idea of holography is more general than, say, the examples that we know in the ADS-CFT, and which, as you say, those are dual to conformal theories. But I think the ideas of gauge string duality, as I more generally call it, apply to non-conformal gauge theories as well, like QCD. Um, though we don't have, as of now, a candidate description for even SUN QCD,
Mhm.
non-supersymmetric QCD, let alone SU3 QCD. Um, so that's one part, that I think the idea of holography should be more general and should apply not only to conformal theories. I think what we do know about theories like QCD is that they are conformal in the ultraviolet, that as because they are asymptotically free. So there, in a free theory, you have conformal symmetries, and the conformal symmetries get broken as you go away from the free point. Um, so so the corresponding dual theories may not be exactly anti-de Sitter space-time, but asymptotically anti-de Sitter space-time. At the boundary, they become anti-de Sitter, but in the interior, they're different. So you can still, and there are non-conformal ADS-CFT duals of that kind that people know, which are supersymmetric and therefore or have been engineered by brain configurations in which you can study this behavior. So even say if n equals to 1 super Yang-Mills or n equals to 2 theories of various kinds, you people have studied those. So that by itself shouldn't bother you, the fact that it's not conformal. Um, about the fact about n is equal to 3, in fact, much before the reason Toft proposed this was that he thought, with some reason, some good reason, which was actually later people improved on that, that the if n equals to 3 might be good enough to get a reasonable first approximation to QCD or to SU3 Yang-Mills theory. And that's because in some ways 1 over n square might be the kind of coupling constant suppressing the additional corrections, the 1 over n corrections, and that might be something like 1 over 10 or so. You can at least get a 90% of the way by even looking at the large n limit. And in fact, the large n limit did explain many features of QCD, and some simple models that people used in the 1980s to study the proton and various features of the proton using protons, and also some the mesons, etc., using large n ideas, were fairly successful in capturing semi-quantitatively the features of QCD. But as you said, maybe what you were maybe alluding to is more some of the work that people have been doing in the context of this ADS QCD or holographic QCD in after ADS CFT, which have which are more should be thought of more as some kind of models for QCD. They're not maybe first principle derivations of the holographic duals for QCD, or I mean the string duals for QCD, but there are some ways to kind of maybe capture with some maybe in an uncontrolled way, but at least give you some kind of a qualitative picture of QCD through gravity. And I think it has had some amount of success. And perhaps one of the most impressive things is regarding finite temperature QCD, where the behavior of the quark-gluon plasma that people have been finding in colliders has has behavior which is not very far from what is suggested by n equals to 4 super Yang-Mills and related theories in terms of this viscosity to entropy ratio, which determines the hydrodynamics of the quark-gluon plasma. So sometimes you may have to be bold and take a leap to, and then try to, may not be completely justified as it stands, but you may get somewhere and then you can try to correct it.
Okay, so let's come to some of the work that you have done, regarding tensionless strings on ADS3 cross S3 cross T4. So a lot of work has been done on finding the CFT dual of strings on ADS3 cross S3 cross T4, and in some particular cases, so correct me if I'm wrong, but in some particular cases we do know the dual. For example, if you have minimal NS flux, so the Navier-Schwarz flux, which refers to something like level 1 in the WZW model that arises in the world sheet theory. We do know that the CFT dual is something called the symmetric product or bifold in the large n limit, where n is the number of copies that you have. And if I'm not wrong, I think this tensionless limit only arises for k equals 1. And but if you go to higher levels, then you don't have this limit. So I want to ask you that. Does this limit makes it easier to understand this theory? And if you go to higher levels, does it become difficult? And the second question that I want to ask you is that whenever when we talk about these gravitational duals, on ADS3, um, I don't know if it is specific to ADS3, but the thing is that we get these higher spin, theories on on the ADS side. So why do we need these higher spin theories, and how what motivates their existence on the gravitational side of the theory?
Yeah. So to answer your first question, uh, higher levels, the level that you mentioned is actually a quantized level in the case of this Neveu-Schwarz flux. And so k equals to 1 is very special, has some very special properties, which is what we used and exploited for the duality to this symmetric orbifold CFT, which is in a sense a free CFT. It's as close to a free CFT as you can, like in a free Yang-Mills theory. Uh, so so that's what is special about the k equals to 1 theory. And it doesn't have some of the problems that are there for higher integer values of k, where this dual CFT actually has some singularities. It has a kind of continuous spectrum and other features which are make it more difficult to analyze. So one should view the k equals to 1 theory as a starting point, because the symmetric orbifold theory can then be deformed. And it can be deformed in multiple ways, not only by having higher NS flux, but it can be deformed in continuous ways by turning on something else called Ramond-Ramond flux. And that in fact, continuously deforms the theory to a very large radius ADS, very far from this tensionless limit. So you can do that, and in fact, we have explored that in a paper about a year ago, how some interesting features of the symmetric orbifold can be studied uh, in the presence of this deformation. So I think the k equals to 1 theory gives you just like the free theory, it gives you a sort of an anchor, and from there you can proceed to deform it and try to study that in different ways, you using other techniques. And many features like the supersymmetric quantities you can study even in the free theory, and try to, because they are often protected and independent of the coupling. So that's one reason why it's very useful to have this special point. It's true that the higher level k equals to 2 and so on, there are proposals for the dual CFTs. They happen to capture, I think, some of the features of the dual singular CFT, but they are much more difficult to analyze. So that was the first part, I think, of your question.
Yeah,
And
before you go to the second part, can you explain if there is any significance of the tensionless limit in this context?
so the tensionless limit, in a sense, can be viewed as the point, and in a way it ties to the second question. It's the point where there's enhanced symmetry in the string theory. It's the point, it's the analog of the massless limit in a quantum field theory. Very often, a quantum field theory, when some of the excitations are massless, then you gain additional symmetries. So the tensionless limit is morally the analog of that, but it is a much more complicated limit. And in some of the cases that we do understand, we do know that it has higher enhanced symmetries. These are these higher spin symmetries. So in a way, I think it answers your second question, um, that there seem, and people had speculated even before the ADS-CFT duality, that the tensionless limit is a highly symmetric point of string theory, where you will have many more unbroken symmetries which would normally have been Higgsed, so to say. Uh, uh, these because string theory anyway has higher spin excitations. In the excitations of a string, you will have higher spin particles carrying many tensor indices, but they're typically all massive. in the tensionless limit, what happens is many of these higher spin fields become massless. The analog, they become kind of gauge fields. So there are higher spin fields which are massless and can be viewed as new gauge, unbroken gauge invariances. And this the nice thing about the ADS-CFT correspondence is that this is mirrored on the gauge theory side as well, because in a free theory, there are additional conserved currents. There are additional global symmetries in the field theory, which translate to gauge invariances in the bulk theory. Uh, these additional higher spin fields are also higher spin conserved currents in the dual field theory. Even if you didn't know about higher spin fields, massless higher spin fields in the string theory, ADS-CFT correspondence would have predicted it, because it would have told you that there are these higher spin conserved currents and they should correspond to massless fields in the ADS, higher
Right.
spin fields. There's a nice matching of these phenomena, and it's at the tensionless limit that you see this matching.
So I have asked this question to some other academics as well, but if I'm totally honest, I don't think I got a totally satisfactory answer to this question. So you have these massless higher spin fields on the ADS side, right? How does that not violate Weinberg-Witten theorem?
Yeah. So firstly, these are not being built from, I mean, the Weinberg-Witten theorem was the statement that you cannot have, say, graviton, a massless graviton as a bound state of some, in some quantum field theory from some fields of spin less than 2. Uh, um, Firstly, it used very strongly facts about the four-dimensional Lorentz symmetry and local Lorentz invariance, I think, in proving this statement. And secondly, the phenomenon that happens here is not that the gauge theories, that the graviton or the higher spin fields are composites of some fields in ADS. They are they are dual to some they are dual to some currents in the boundary CFT, but that's in one lower dimension. So the Weinberg-Witten theorem never told you that you could not consider a graviton in ADS5 as coming from some bound states in the boundary theory. That's
Okay.
outside the scope of the Weinberg-Witten theorem or what it proved. It was purely a statement in four dimensions or in any space-time dimensions, primarily four, but I think you can generalize it, of the graviton in four dimensions arising from some field theory in four dimensions as a bound state. So here we shouldn't think of the massless higher spin fields as bound states of some things in the ADS.
Mm-hmm.
At best, you can think of them as some kind of holographically, they can be described by something in one lower dimension. So it's not quite the same.
Okay, I
If
see.
that makes sense. But yeah, so the Weinberg-Witten theorem is in a way evaded even by the graviton. I mean, in ADS-CFT, the graviton in the ADS is arising as the stress tensor of the is kind of coming, can be viewed as the excitations of the stress tensor of the dual CFT. And but it's not the stress tensor in the ADS spacetime.
Right. Okay. So correct me if I'm wrong. So this, when people talk about these higher spin, fields on the ATS side, they refer to this theory called the Vasiliev theory, right?
Right.
And according to what I understand, Vasiliev didn't make this theory motivated by holography or something like that. He
Right.
just made the theory because he thought that this is consistent, right? So, did he make this theory to evade Weinberg-Witten theorem, or was the motivation something
No,
else?
no. He didn't make it to evade Weinberg-Witten theorem. He made it to evade another no-go theorem. I think it was by deSitter and someone else, I think, which is that uh, you cannot have massless higher spin fields in flat spacetime, in asymptotically in Minkowski's spacetime. You can't have interacting higher spin fields, which also which have higher spin gauge invariances. Gauge invariances higher than spin 2. Uh, so there's a Weinberg theorem which tells you that you can't have conserved quantities in flat space of higher spin in dimension greater than 4 and so on, greater than or equal to 4. But and the kind of related to that is the fact that people showed that if you try to write down a Lagrangian for, say, a massless spin 3 field with a spin 2 gauge invariance, I mean, with a gauge invariance the analog of diffeomorphism, if you try to write down a Lagrangian at the interacting level of such a theory, and especially when you have to couple it to gravity, because everything couples to gravity, you can't write down a consistent Lagrangian in flat space. But what Fradkin realized, I think, and Fradkin and Vasiliev, so Fradkin was the first person, I think, who realized that you can evade this theorem, this deSitter no-go theorem, in anti-deSitter or deSitter spacetime. If you have a cosmological constant, if you have another scale in the theory, like a cosmological constant, you can evade this theorem and have interacting Lagrangians of higher spin fields. But what they found was that you can't just add one field, at least typically not in 4 dimensions and higher. You can't just add one field. You have to add a whole infinite tower of them. And Vasiliev constructed this tower and its interactions systematically. And in ADS3, you can evade it a bit because things are a bit topological in ADS3. So you can have a finite tower. You need not have an infinite tower. So that's a special feature of ADS3. But in general, so that's what one is trying to evade. How can you have an interacting theory of these massless higher spin fields with their gauge invariance? It's the gauge invariance which makes it tricky to have interacting theories, because you want to be able to write down a Lagrangian consistent with that gauge invariance and diffeomorphism invariance. So you have to have a combination of all of these very big gauge symmetry or gauge
Okay,
invariance.
I see. Okay, so I want to talk about another piece of work that you did in the late 90s. So let me give a brief description of that, and you can add to that description later. So when one way to make 6-dimensional Calabi-Yau manifolds, which are known as Calabi-Yau threefolds, um, you just write down this quadric, that some people refer to, and set it to some complex number. And the thing is that when this complex number becomes zero, there is this transition called the conifold transition, right? So you can write down, a string theory, a topological string theory on this conifold. And what you discovered in the late 90s with Wafa is that if you write down Chern Simons theory, which is, a gauge theory on, 3-dimensional sphere, which is called S3, then it is kind of the same as topological string theory on this conifold geometry. And I think in a podcast you said that you were calculating things and things matched on both sides. So I guess that this is the work that you were referring to. Correct me if I'm wrong. So how did it feel when everything started to match on both sides of the I don't know how to say this, both sides of the canvas probably, because I think you said that you verified that things matched in all orders of 1/n. So can you tell us a bit about that piece of work?
Yeah, so that again was a very simple gauge theory, this Chern-Simons theory, but it has the advantage that it had been solved by Witten completely, and you knew how to take its 1/n expansion. Actually, it was a little tricky. It's a little different from how people had actually taken it before, but nevertheless, it was a well-defined question, and something like the partition function or the free energy, you could study it exactly. And in the dual side, the conifold side also was simple enough Calabi-Yau geometry that due to some things that Kamran and I had figured out, we could also say what that was to all genus in the string. And it's a topological string theory, so it's also a simple system to study. So it was rather a miracle that these two things should match, and in a way that was a very important. I mean, it makes you feel that you've glimpsed something very special when you see something unexpected like that, and so it certainly was one of the most memorable experiences of my life to have sort of glimpsed that. Yeah, so but it also gave you a lot of confidence that ADS CFT or gate string duality is really, I mean, it's not some thing that's just some words. There's some real reality to it. Even if it's a mathematical reality at some level in this case, but it's saying that these two different theories are the same secretly, and that gives you confidence that this is a very general phenomenon.
Right. Okay. Okay. So I think we have two more questions. Then I have some questions from the people, and then we can finish it. So you are the director of ICTS, and this is a position where you have to do a lot of administration. So after becoming the director of ICTS, were there some challenges that you faced that you didn't face as an academic, but now you are facing them as an administrator?
Yeah, in fact, I don't see myself as an administrator in a sense. In a way, I took on this position of being heading this new center. It's a brand new center. I mean, it was when I took it. Now it's some years, but I see myself as a kind of it's an part of an act of public service. That it's more that here's an institution which is meant to nurture scientists, it's meant to nurture scientific temper, it's meant to sort of push science ahead in India and the world, and create an environment that can allow for that. And so I see myself as more, in that sense, being facilitating something and knowing what I think I try to bring to it some knowledge of what it takes for science, for creating an environment where scientists can do very good work, where they can be stimulated, where ideas can be exchanged, where new things can come out. So it's more like the job empowers me to try to create that atmosphere. And that's my main goal, in a sense, that I see as my main goal, to sort of make sure that all the faculty, students, visitors, programs, and so on are of the highest intellectual quality, and in a way that people who are there can think big ideas, think of important new thoughts, which will push science ahead. So in that sense, So I don't see myself, and I wouldn't do this job if I had to just, be a Sarkari Babu. But
Sure, sure.
I would. So it's because there was a possibility, and I think I have been seeing that happen to do all this. That was close to my heart. That was one of the reasons that I came back to India to do that. And so this enables me to do that. Uh, Another analogy I often use is that my job is more like an orchestra conductor. There are all these uh, brilliant musicians all playing their different these things, and you want to kind of make something collective out of it through and that's what an institution does. That's such that it becomes more than the sum of its parts. That's at its ideal in an ideal setting. That's what an institution should do.
Sure. So yeah, it's great to see that you see it in this way. But the thing is that when you become, the director of an institute, there are some challenges that will come your way, no matter if you
Right.
like them or not. So, for example,
Right.
I talked to Fernando Quevedo, who has been the director of ICTP for 10 years, and he
Right.
said that one of the biggest challenges when he became the director was that how to get funding for ICTP. So, did you feel any kind of pressure like that?
Yeah, so there are challenges, but it's like in anything in life, right? I mean,
Mhm.
you're living, you have challenges. I mean, they all vary in different. It's a matter of scale and a matter of degree. Uh, uh, so, so we are not kind of just abstract beings who are only focused on our work. I mean, we live in societies, complex environments, and we navigate them. We have many different things to do. So sure, you have to, and when you have certain responsibilities, you have to navigate them. And indeed, funding for science is an important challenge. And in India, that is something we have to constantly have to make the space for that, and you have to really ensure that the science doesn't suffer, and that, or rather, you have enough resources to be able to do some of the things you can, but at the same time be also accountable for the funds that you're using, because uh, there are many needs in a society like India's, and the fact that the society has supported science for in a fundamental science is I think a very positive thing, but it should not be taken for granted. But at the same time, you should, and those who are scientists have a responsibility, I think, in India to deliver, to kind of do the best that they can do, and so yeah, so it's both sides of the coin. So so yes, so I've also had to the funding challenges, I think, are universal even in the US.
Mhm. Sure.
The people have to struggle for things, and it's part of uh, the price you pay for the privilege of doing the science you enjoy. Mm.
Right. So, in your experience, being the head of an institution, does that significantly impact the time that you can give to your research?
It certainly does take time, and I did have to. I mean, you do sort of sacrifice some of the additional time that you would have had. That does go away, but uh, it's a. So I've been trying, I think, to keep a balance,
Sure.
and working with very good collaborators and keeping that up and utilizing my time in some optimal way. I think I've managed to balance it reasonably, but yes, of course. But it's, you have a family, then also time goes in that. But it's like in life, you have to balance many things, and you try to apportion it in some way that it doesn't significantly impact what you want to do many things, but you have a 24 hours in your in a day, and you have a finite amount of energy, and you have to try to optimize that. But indeed, yeah. But there are other things also, I mean, which I enjoyed. I used to enjoy teaching at HRI when I was before there, but I don't teach right now. So that helps me save some time in that, but so I don't have those teaching duties. So yeah, so there are some things that you do and even in any faculty member has to do some amount of work for the institute. So everyone balances these at different levels. But
Sure.
it's true that I have probably more than my share of it, and but I also try to kind of delegate many things, and I think my
Okay.
colleagues at ICTS are wonderful people, and they've been all supportive, and I think we try to manage it as a team.
That's great. Okay, so I have one more question before we go to people's questions. So the question is that, what factors do you consider before taking a PhD student?
Oh, before taking a PhD student, especially since it follows on your previous question, especially in my current this thing, I certainly expect my PhD students to be a little independent, and I discuss with. I mean, I don't have that much time as I used to have before to discuss with them, so I think that is something the student has to be prepared to live with, and be independent, also talk to other people, yeah. So I think I expect them to have their basics very sound in quantum field theory and general relativity and some of the ideas that are there in string theory. But other things I think they pick up on the way, and they should have a certain wavelength match with me. I don't uh, often. I mean, sometimes many of the problems I think about or I suggest are not very feasible, and so they have to be prepared to sink in some amount of time and not make much progress, I think, and that's always the case in science. And I think for students, it sometimes is a little difficult for them to this thing that they've spent, I don't know, 6 months, but it's not going anywhere. And that happens, and I think you should live with it. I think if you only worked on very determinate problems, you know what the answer will be. You just have to go through it and calculate it. Then I think that removes the interesting thing about science, the unpredictability of the indeterminacy of the outcomes of your work. So so people have to be willing to put up with some, I think, have a bit of that mental strength to put up with explorations. I realize, of course, the PhD time is limited. It's 5 years or so. They have their this thing.
Mhm.
So yeah, you have to, but 6 months out of 5 years is okay. And who knows, many of the things you learn there will be things even if it's a failed venture, you might learn things which might come in later, or you might revisit that problem later. So, uh,
Right. One question, one follow-up question that I may have here is that, the trend that you're talking about is very, prevalent, and I've seen many manifestations of that. That a lot of people work on problems that they think that they already know the answer to, and they're just deriving that answer. But a lot of people do that because they want to have more papers because of the bad job market. So don't you think that that particular thing plays a role?
yeah, I understand the psychology. It definitely plays a role, and I think it's not very healthy for
Mhm.
science for that kind of thing to be prevalent. There has to be some balance somewhere. I think one has to. I think perhaps the balance has shifted a bit too much on the paper writing side for the sake of writing papers, but
Yeah.
it shouldn't swing to the other side also, where you can very easily tell yourself, oh, I'm thinking about some deep problem, so I'm not going to publish it on anything until I solve it, like Andrew Wiles did for 7 years. uh, um,
Sure.
so it shouldn't go that way, it shouldn't go this way. You have to find some equilibrium in between. And yeah.
So, do you think that senior academics can take some steps to curb these kind of trends?
Everyone can do some things within their limited domains of influence, I think. I mean, because each country typically has its own funding patterns and things. I think at ICTS we have tried to keep things a little bit insulated from that, because the nature of our funding and other things allow us to be a little more adventurous in selecting postdoctoral candidates and so on. So we don't typically just go by just the number of papers and so on. We try to yeah, I think we try to be a little bit not driven by fashions or by hot topics and so on. And
Right. Okay.
uh,
Okay. Yeah. Please go on.
yeah, so I mean, so you can do it like so you can do it within your domain, but it may not be globally applicable. Um,
Sure. 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 Okay. So I have some questions from the people. People ask me some questions when I announce this podcast.
I see.
So let me just ask those questions and you can answer them. So the first question is that how do you see the interplay between mathematics and physics evolving? Will increasing mathematical sophistication continue to guide physics, or do you envision data-driven methods like AI taking a more prominent role?
I think the two aren't mutually exclusive. The
Hmm.
two options that were
Yeah.
mentioned aren't mutually exclusive. I think the mathematical sophistication will definitely increase, and because that has been the way. I think more mathematics has also sort of developed very deep, subtle conceptual structures. Physics, at the same time, has had also needs, I think, subjects like string theory and even subjects in condensed matter physics have needed very sophisticated mathematics. But At the same time, physics has also been giving to mathematics, and it's become a more a two-way exchange now, and that's very healthy, I feel. And I think that trend will continue. I think there was a bit of a divorce between mathematics and physics in the middle of the 20th century. I think that has probably gone, and there's much more give and take between the two communities, which is very exciting, healthy, and just wonderful. Um, but About the AI-driven methods, I think in a way, maybe, I mean, it's so early and so rapidly changing that probably any prediction is going to be very foolish. But It may well be that the increasing sophistication uh, is helped by AI methods also. I mean, it's just like Mathematica has liberated people from just having to do some integrals or more routine things. Maybe again, some of the ideas here can be probably carried through by AI, but then you might I like the idea that some people float that AI and human creativity, at least in mathematics and related and perhaps theoretical physics, can have a much more kind of synergistic kind of take a synergistic form in which both sides kind of complement each other, and uh, and people are forced to now think about things which AI can't think about. I mean,
Hmm.
Mathematica didn't change. I mean, it's not like it put people out of business. Of course, we are talking about something at a different scale here, but uh, I feel the thinking will adapt in a way that will take into account the AI, the inputs that AI can give you. and humans will adapt in a way that will take those and take the whole thing to a next level. And so, in a way, the two options might very nicely feed into each other.
Okay. So the next question is that what do you think are the key phenomenology approaches right now, and how is India doing in phenomenology generally?
I mean, I'm not an expert in
Mhm.
phenomenology and I don't want to say very much there, but in general, particle phenomenology, I think, is definitely at a crossroads in the sense that in the absence of new significant experimental input, uh, things have, I mean, it's very difficult to kind of make progress in at least the traditional areas of collider physics. I think some of the interesting areas worldwide are in other things which don't involve colliders, even maybe many other kinds of tabletop experiments, other uh, mm, many new innovative ideas, which like people looking for axions, dark matter, cosmologically and astrophysically, and again neutrino physics, and so on. I think there are these other options which people will probably explore much more uh, compared to the traditional collider physics. And in India, there has been traditionally a community. I think it was largely focused on collider physics, though the substantial number of people in neutrinos and other areas. I think the people are also evolving with the subject worldwide. And
I see.
I think trying to take the subject forward. But I think some good experimental data breakthroughs will be very important, I think.
Okay. So the next question is that why is a lesser number of people working on deSitter spaces?
Well, there are some major challenges there. I think to understand string theory on digital space is not easy to formulate because it's not directly a solution of background of string theory. You can have it as maybe a metastable state in string theory, and many people are trying to now construct digital vacua with some amount of success, starting from regular string compactifications. So yeah, there are, I think, some conceptual challenges there, and in general, time-dependent backgrounds like deSitter are difficult to study in string theory, and we think we haven't really um, sort of tackled it full on. So there's a scope there. I think it's a scope for whoever asks the question to try to tackle these problems. Yes.
Okay. So so this is a bit of a critical question. So the question is that what is the thought behind ICTS not providing a master's program, not integrated PhD, unlike many institutes?
It does provide an integrated PhD program. People do come after their bachelor's and then do their uh, kind of get a master's come PhD
No,
at
no, they're saying that just masters and not integrated PhD.
Oh, just masters. In principle, people can leave after their master's
Mhm.
degree. I think TIFR, I mean, we are part of the TIFR system, and academic sort of the TIFR is a university which has its own academic kind of requirements. So we have to abide by the broader TIFR academic requirements, but people have left after a master's. It's true that we don't have a purely master's program. I think that firstly, we don't have the number of faculty to teach a full set of courses that you would need for a master's program. And I think right now we have in the physics faculty, maths is even fewer than physics, but even with the physics faculty, it's not very easy. Though there have been discussions within the TIFR system of having master's programs, so it may well happen in the future, especially as our faculty strength grows. It may yet happen. There's nothing in principle that we are against it or anything. It's a matter of logistics. You have to do many other things in terms of housing, many other things will also. Uh,
I see. So you're saying that you can leave after your master's when you are in the integrated program, right?
in the integrated program, in principle, you can leave after a master's, but typically you finish the master's requirements after 2.5 years or so. So it would take a little longer than a conventional master's. And that's why I think most people feel it's beneficial to just continue on to a PhD. Uh,
Okay. Yeah, I wanted to address this question because multiple people asked me this question, so I wanted to
okay,
address this. Okay,
I see.
so I think we have three more questions, and then we can finish
Okay.
this. So one question is that since you also come from Calcutta, were you inspired by Ashok Sen when you were young to come to physics?
So I grew up in Calcutta, but I think at that time I had not heard of Ashok Sen when I was in school. I mean, because in fact, I think when I was in high school, that was 1987. I think at that time Ashok has probably just finished also his PhD and was starting
Hmm.
as this thing. So he had not yet done some of the very famous work for which really changed this thing. So definitely at that time I had not heard of him. It was only much later, I think in 1991 and something that I had, and then I actually took some winter school that he taught. On CFDs I had attended in 1992 but I was in my final year of my master's program there.
Okay, so you heard about him when you were a graduate student, right?
uh, when I was an I mean when I was in my third year or fourth year of my undergraduate studies, I did this 5-year
Okay,
program.
I
So
see.
it was sort of midway through that I
Okay,
uh, knew
so
of it.
so this
But
next
Ashok,
question.
I think people may not know, but I mean, some of them, he had done already some very important work by at that time, but some of the really, the work for which he's really most renowned for involved the strong-weak coupling duality that came by at the time of the duality revolutions and so
Mhm.
on when I was a graduate student. So this was it was that came much after when I was an undergraduate or a school student.
Okay. So this next question has a bit of an introduction. So it says that when you are in undergrad, you have to solve textbook problems, which takes at most some hours. When you become a graduate student, you have to solve textbook problems, which are a bit harder, which may take sometimes weeks or but not more than a month or so. How to go from that mindset to a research mindset where problems can take years to solve?
Yeah, it's not easy to make the transition. You have to firstly have patience and that kind of uh, also perseverance, not wanting to let go of something. If you're unable to solve it, it should just keep going on in your head. Sometimes you have to leave it aside. I mean, you can't keep banging your head against a wall if you're stuck. Uh, you have to be able to let go, maybe do two or three things at a time. Uh, Often, I think many people enjoy teaching because it enables you to sort of do something else when you're stuck, and it kind of resets your brain in some way, and then you come back and you have fresh ideas. So you have to keep you shouldn't mentally kind of stagnate. You need to find ways to make some progress so that you feel at least psychologically that you're making progress. It may be small incremental progress every day or at least over a week or a month or something. You should feel you've made some progress, even if not. indirectly towards the original problem, towards some side thing, something you understood, something you, I think, so if the original thing doesn't work, you have to try to kind of reformulate things, try to look at other things. So yeah, you have to be a little opportunistic, a little bit. Uh, it's difficult to characterize it, but yeah. But I think some of the things I mentioned are definitely qualities you have to cultivate. I don't think it's anything you can't cultivate. You have to develop an attitude which adjusts to that time scale.
Mhm. Okay, so last two questions. First question is that academics tend to be very competitive, but is it a healthy attitude to compare yourself with other scientists all the time?
Yeah, definitely not all the time, I think, and people get too caught up in that. If you get too caught up in that, I think that's not going to keep you, that's not going to help your creativity, I think. Of course, it depends on people's temperament. I think some people are innately very competitive, and some people prefer to do things their own way. And the nice thing about academics, and I think in a subject like string theory and so on, is that there's space for a lot of different kinds of temperaments, a lot of different kinds of talents and strengths. You have to, what is more tricky is to find the problem, and this in a way addresses the previous question also. You have to find the problem that you have the right strengths for. You should be able to identify that fairly accurately and be honest with yourself. So I think if you're just comparing all the time, those are not those are not accurate, because other people are other people. They have their strengths, and they have their weaknesses, and your strengths may not be their strengths, and their strengths may not be yours, and so they may achieve progress in something that's good. You try to find the problem where you can make progress. I think that's the main thing, that you should be benchmarking yourself in a way. You should feel that you understand something better today than you did last year, or some things. You have made something better. So I think it's ultimately, I think that's the healthiest way in which you can grow your intellectual capabilities. And it's because comparing with others, I mean, it's at some level human and inevitable, but you shouldn't let that kind of take over your thinking.
Sure. Okay, so the last question from the people is that how to deal with failure as an academic?
Yeah, I mean, of course, failure as a human being is a broader question. I think you can ask, because that applies to everyone, I think, and some people deal with it better than others. Some people, I tell people that, take failures as a this thing that, I mean, at least mistakes that you make, you should take them as opportunities to learn to try to extract at least some lesson from it. That okay, maybe it was too tough a problem. Maybe that was not. Maybe I shouldn't have spent all that much time. I mean, try to extract some lessons from what you this thing, instead of just obsessing over the failure part of it. And as I said, when you're a graduate student, you should be prepared. And I think it's a good training for you to work for 6 months on something and not make progress on it, and just not really. It is useful because it tells you that you should be makes you prepared for failing at some of the research problems that you're doing, and it does it at a stage when you're still a graduate student, and you have still some time. And so of course, if you spend 2 years and then you're not then you have not made progress, that's more serious, because that can have a major impact. So you have to know uh, when to kind of stop, so to say, or to change tracks. So So, and that's a lesson you can learn from a failure. I mean, maybe you spend 1 year where you should have stopped doing that problem after 6 months. So, yeah, so I think you shouldn't let your failures define you. Everyone fails, and you shouldn't let that kind of overpower your thinking. Shouldn't make you kind of lose your self-confidence. I think it's important to keep your passion. Why are you studying the subject? Why are you working on this? I think it's important to keep your motivations in front of you
Mhm.
all the time, so that you realize what are your basic fundamentals, your core beliefs. You shouldn't
Right.
let that get affected by failure.
So do you think that one thing that we can do is that we can talk more about failure, in the academic discourse, so that people can understand that this is normal? Because the thing is that a lot of people tend to think that this is a very abnormal thing that is happening to them and
Exactly.
they are failing.
Exactly. I think it's very important. Yeah, people talk about. I mean, when I say 6 months, this thing. I mean, I'm speaking from personal experience as well. I tried many things in my PhDs. The first problem that David Gross set me, it's a problem I would like to solve, but I still have not solved. I mean, after so many years, but no one has solved. So so you have failures, but at that time you think, oh, okay, maybe I shouldn't have I mean, but that led to something else, and then you realize that okay, you still learned something from that experience, and yeah, I think it's important to talk more about failures, and it not kind of feel that it's something individual to you. Everyone, I think, fails. It's only how you deal with the failure that differentiates people.
Okay. So yeah, so our questions are over. Thank you so much for your time. It was great to talk to you, and I hope
Not
that we
at
can.
all. Thanks very much for a nice conversation, and all the best.
Thank you. My pleasure. So if you like this video, give it a thumbs up and consider subscribing, and the YouTube algorithm thinks that you will also like this video.